Now, so we had already stated that we'll be looking at elliptic curves, especially those that are applied in real life. And we had begun looking at Montgomery as one of those elliptic curves we'll be looking at. So this is where we left last times before we went for a short holiday. So just want to remind ourselves what we looked at on the elliptic curves generally, and then on the Montgomery as we go forward. And we said, well, after this, we'll be looking at pairing cryptography and every other, every other applications of elliptic curves in cryptography. So those are the things we'll be looking at before we proceed to lattice-based cryptography. So on this Montgomery, just again, to remind ourselves on the definition. And of course, we are defining it over a field F. So the definition of Montgomery is slightly different from that of the short Westerese. It is by square is equals to x cubed plus ax square plus x. You remember that the short Westerese will be y square is equals to x cubed plus ax plus b. That is the one for the short Westerese. And so it's different from Montgomery. And what is interesting is as we go forward is how do we convert from one to the other? Supposing we want to use the Montgomery form and we have the short Westerese, how do we convert from this short Westerese to Montgomery and from Montgomery back to short Westerese? So that is the most important thing that we'll be looking at today. But of course, the question is this. This is a question for the Montgomery curves. Now, just as the short Westerese form of the elliptic curves, we require that the equation, for it to be an elliptic curve, it must be non-singular. We require that it must be non-singular. And of course, what this means is that, let me again remind you how we're drawing the elliptic curve for the short Westerese. It was something like this, so that it is symmetric about x-axis, symmetric about x-axis. Now, so we have values that satisfy x, the values of x. So if you are solving for x, for instance, when do we say that it's non-singular? We say that it's non-singular if those values of x are distinct. If they are distinct, you're solving for x, getting the values of x. If they're distinct, then we say that it's non-singular. So if it's non-singular, then it becomes an elliptic curve. But if the values of x are identical, then that equation, that curve is not elliptic curve. It's not an elliptic curve. So that is what you're saying. What I therefore mean that you could find an equation of this form that it does not satisfy this non-singularity property, and therefore it's not an elliptic curve. It's not. So first of all, if you have an equation of this form, I first find out if it is an elliptic curve. Otherwise, there are cases when it's not. If the values of x are identical, then it's not elliptic curve. They must be distinct. So, in other words, it must be non-singular. So how do you find out if it's non-singular? We are using this property. You have the b into brackets s square and then minus 4. If this gives you non-zero value, then it means the values of x are not identical. And therefore, the equation is an elliptic curve. It is a Montgomery elliptic curve. So that's a very important point there. So the important point is that not all equations of this form will be elliptic curves. So you have to, first of all, I find out whether it is by checking whether it's non-singular or not using this property. Now, so why are then Montgomery curves of importance? We are saying that they are widely used in cryptographic applications. And the reason is that it's easier to do arithmetic, whether addition or what. Of course, we're talking about elliptic curves, we'll be looking at how to double points, how to add points. And so we are saying that for Montgomery curves, those operations are easy to perform, and that makes it very much efficient in applications. And that's what I've just said here. That's what I've said, that unlike the general Westerese form, we find that it's simple to carry out addition and even doubling of points. Now, again, the point number 2 here is that we shall not have Montgomery curves defined on every field. It will not be defined on every field, but on some fields. And I've said here that is defined only on fields where the characteristic of f is not equal to 2 or 3. So the characteristic of f should be more than 3. If it's more than 3, then we can define Montgomery curve on that field. I want us to recall what characteristic means, and that's what I put here. By characteristic of a field, I mean a number which, when added to itself, the number of times one will be added to itself to get 0. The number of times one will be added to itself to get 0. That is what we call the characteristic. For instance, when you talk about F5, then we are saying that 1 can be added to itself 5 times to get 0. 1 will be added to itself 5 times to get 0. Mod 5. So 1 plus 1 plus 1, 5 times, it gives us 0 mod 5. That's what we mean by characteristic, and that is, I was just reminding. So we are saying that we can define a Montgomery curve on a field whose characteristic is 4, 5, and so on, but not 2 and 3. Just like the other elliptic curves, again, points on the Montgomery curve will form an abelian group, and the identity element will be the point at infinity. So the points will form an abelian group, and the identity will be the point at infinity. So this abelian group, of course, this is a group under addition. Okay, so let's again see how to convert from short Westerese to Montgomery and back. And of course, we had done this, just recalling, so that as we proceed, we have the basics so that we don't struggle going forward. Now, so if you are given a Montgomery curve, this is the Montgomery curve. Its equivalent short Weierstrass form is this. This is the equivalent short Weierstrass form. Remember, short Weierstrass form is an equation of this kind. So this is the equivalent. If you're given Montgomery curve, this is a Montgomery curve, the equivalent short Weierstrass is this mod G. So that means when you equate, you can see that this is equal. And so it means that our A therefore is this. This is our A. And it therefore means that our B will be this. So it means that if I'm been given this, the short Weierstrass form, the Montgomery, I can easily get the short Weierstrass form just by noting that our A is equal to 3 minus A squared over B multiplied by B squared times 3. And then our B will be equal to 2A cubed minus 9A divided by 27B cubed. So if I'm given that, this one is very easy to convert. So what I want us, although we shall look at this later, but I want us now, how do you convert from the short Weierstrass to that? How do you convert from short Weierstrass? But converting from Montgomery, this is the formula we'll be using. This is the formula we'll be using to convert from Montgomery to short Weierstrass. Now, a very important thing to note here, I've said that not every short Weierstrass form can be converted to Montgomery. But every Montgomery curve will always be converted to short Weierstrass. So if you have a Montgomery curve, you can always convert it to short Weierstrass. The other way around is not always true. You cannot always convert short Weierstrass to Montgomery. For the short Weierstrass to be converted to Montgomery, it has to fulfill some conditions. So only those which fulfill those conditions can be converted to Montgomery. Not every short Weierstrass can be converted. So the conditions that a short Weierstrass form of elliptic curve should fulfill for it to be convertible to Montgomery are the following. One, that elliptic curve, the points, the number of points, the total number of points, or the order of the group formed by those points should be divisible by 4. So what I mean is, if the short Weierstrass form has 12 points, for instance, then this form can be converted to Montgomery. If it has 16 points, it can be converted to Montgomery. And that is not the only condition. That is just the first condition. But that condition already tells us that if it has 15 points, it cannot be converted. So we don't need to check for the other conditions. If it has 17 points, if the short Weierstrass form has 17 points, you cannot convert it to Montgomery. It's not possible. But that is just the first condition. Supposing it has fulfilled this first condition, you check for the second condition. It must also fulfill the second condition. So the second condition is, this was our Weierstrass form. This was our Weierstrass form. Now, if you just take this equation on the right side, this equation on the right side, and equate it to 0, can you find the value of x if you just took this, the right-hand side, the equation on the right-hand side, and equate it to 0? can you find the value of x? If that is possible, then this Oyster form has a likelihood of being converted to Montgomery. And that is the point I've said here. I've just extracted the one on the right side. Of course, I changed it to Z. There's no problem. You can even work with X. And the question is, does this have a root? Does it have a root? Can you get the value of X? Can you get the value of Z? If it has a root, then the second condition has been met. You proceed with the third and last condition. You proceed with the third and last condition. The third condition is that now that there's a root, you've obtained a root. You've obtained a root. Now that there's a root, take that root, square it, and multiply by 3. And then add A. A is just coming from the equation. A is just coming from the equation. Add that A. And then the answer that you get, the question is, does it have a square root? The answer that you get, does it have a square root? If it has a square root, then this equation has met all the conditions. This Oyster form has met all the conditions. So the first condition was, look what it's, how many points does it have? Are they divisible by 4? If they are, proceed. Take the equation on the right side, equate to 0. That polynomial on the right side, equate to 0. Can you get a root? Can you solve for x? Does x exist? If the value of x exists, the second condition will have been met. Now take that value of x and square it and add it to multiply by 3. And then add 1, add A. Can you get the square root? Does the square root exist? If the square root exists, then the 3 conditions have been met. Now, so if those 3 conditions have been satisfied, then we say that Oyster form can be converted to Montgomery. So now, how do we convert it, therefore? The first thing was to establish if it can be converted. Now that we've established, how do we convert it? The first thing for us to convert is to find x, the scaling factor. To find the scaling factor, S. How do we find S? Our Oyster form was y square is equals to x square, x cubed plus ax plus b. Take our S, therefore, is the square root of 3 multiplied by a, this a, 3 multiplied by a square, then plus 4b, plus 4b, this b. So just using the short Oyster form, the square root of that, after getting the square root, the inverse, it in fact is the inverse of the square root. Is the inverse of the square root. Take the square root, and then the square root has 2. The square root of a number has, so you pick one first. Suppose the square root is 3 and another one is 4. So pick 3 first, and then get the inverse of 3. Now, once you've gotten S, you can straight away write the Montgomery equation. So the Montgomery equation, therefore, is times y square. Of course, it's supposed to be b y square equal to x cubed plus a x squared plus x. This is how it is. But now we had the short way stress and we have our s. So instead of b, we just written s y squared. Then there's x cubed. And then where there is a, our a is equals to, our a is equals to this square. Is equals to 3 z naught. Remember, z naught was our value of z here. So 3z naught times s, then multiplied by x, and you square the whole thing. In fact, this is just the same as, this is the same as x cubed plus 9 z naught square s square, then x square, then plus x. Is the same thing. So this, therefore, is our Montgomery form. If you had the short way stress form, this is the Montgomery. Now, you can see converting from a short way stress to Montgomery is not a lot of work. The only place where there is work is, first of all, finding out whether the short way stress form can be converted. This is the only place we have work. Finding out if the short way stress form can be converted to Montgomery. Once you find out that, whatever remains is just one step. You're only required to find s, which is the square root, and the square root of this, the inverse of the square root. The inverse of the square root. And then once you have the s, you just substitute in this formula. So I'll take an example. Take an example just so that the steps are clear with us. I'd already said that S is the scaling factor. And what its role is just to normalize the curve. And why are we normalizing the curve? Just to ensure that quantities like addition and doubling of points will adhere to the curve. So that when you add those points, you find that those points are, of course, on the curve. The result will also be on the curve. So just to normalize, that is what the scaling factor does. Now, we look at this example. Now, been given prime is 17, the prime that F17, and the elliptic curve, this is a short way stress. Of course, at your own time, you can determine whether it's an elliptic curve by just ensuring that it is non-singular. Now, determine whether this elliptic curve, this short way stress, this is just the same as this. So it's short form of this. Short form of this, where 8 here is the A and 2 here is the B. So that if somebody writes this, you can then know that this person, what elliptic curve is this person referring to. If somebody writes this, you can of course know that this person is referring to y square is x cubed plus 8x plus 2, and of course is working mod 17. So just a short form of writing this one. Of course, several books will have different short forms of doing that. What is important if you are reading a book is to get to know the notations the book is using. Now, so we have this short way stress form. And the question is to determine whether it can be converted to Montgomery. And if so, we convert it. That is what we're supposed to be looking at. So the first thing for us to do is to determine whether, how many points does it have? To determine if those points are divisible by 4. And this you can use our code for finding our Rust code for determining the order of an elliptic curve. Okay, so I did that and I discovered that this curve had 16 points, has 16 points. And the 16 is divisible by 4. And therefore, that means the first condition has been satisfied because the curve has 16 points, which are divisible by 4. You don't stop there. We have two other requirements that it must meet before we say it can be converted to Montgomery. So the other requirement is to take the polynomial on the right side and find out whether we can solve it for x. So the polynomial is this on the right side. So we want to determine whether you can solve this polynomial and get x if you equate to 0. Can you find x? And of course, you are doing this mod 17. Can you find x? Now, this you can use Rust code to do that. So what will Rust code therefore be doing? Just be checking values between 0 to 16, mod 17, checking which value, if placed here, would fulfill, will give you 0. So for instance, since we are doing it mod 17, we've said, want to see which of these values, is a root. We want to see which is a root. That means which one, if substituted for x, would give us 0. So you begin by 0. Let's check 0. You check 0. The 0 cubed plus 8, 0 plus 2. And you can see that this is not equal to 0, and therefore 0 is not a root, because this will be 2. Then you check 1. That will be 1 cubed plus 8 multiplied by 1, then plus 2. And this is, it looks like 11. Is 11, which is not equal to 0. And therefore, it means 1 is not a root. So that is what the Rust code will be doing, therefore. Checking all this. And when you check up to 8, I checked up to 8, and 8, I found that 8 was a root. 8 was a root. So in fact, 8 cubed, 8 times 8 plus 2 was giving me 0. We are doing this mod 17. This was giving me 0. Then manually you can still do it. Because 8 times 8 is 64. Times 8. And then plus 8 times 8. Then plus 2. 64 divided by, just reducing that, you can still multiply it by, and remember we are doing it mod 17. So 64 divided by 17, of course, goes there 3 times. That's what I'm getting. Goes there 3 times. And the remainder is 13. So this is like 13 times 8. Then this is 13 because it's 64. Then plus 2. Of course, 13 and negative 4 is the same thing. 13 and negative 4, they're congruent. You can also say it's negative 4. There's no problem. But what is 13? Let's just use 13 times 8. I'm getting 104. Then plus that 13. Then plus that 2. I'm getting 119. 119 divided by 17 goes there 7 times. The remainder is 0. 7 times the remainder is 0. So 8 is a root. So the second condition has been satisfied. What is the third condition and the last one? The third and last condition is now to take this root, multiply by 3, and then add a to the result and see whether the result that you get has a square root. Okay, so we found our root, 8. Now square that 8, multiply by 3. That is 64 multiplied by 3. Then add a to it. Our a in this case is 8. Our a in this case is 8. So this will be 64 times 3, which is 200. And when you divide by 17, the remainder is 13. The remainder is 13. So the question is, does 13 have a square root? Mod 17. Does it have a square root mod 17? Now, when you do it using your code, let me see whether I can open my code, but I think I've done it earlier. Let me see, let me just open my code. Now my code is a bit, is not here, I not opened it earlier. Usually I open them before the class so that they are ready. But the code for finding the square root, we had already done that. That is modular inverses. Let me just see whether I can get it here. Just a short while. Yes, I found it. Modular inverses. Let me now share this code. Okay, this is the code for finding modular universes, and I want to find the modular universe of 13. Okay, let me see what it is. You can see my code, huh?
Yes, you can see it.
Oh, but this one is not the one. This one is additive. I think I opened the additive because it's giving me the modular inverse of 13 to be 17. This is the additive one. I wanted the multiplicative. Will this be the same thing? The same thing. Let me just look for it a short while. The one I got was additive. Just to save on time, since I've already done it, and since we already saw that code, we had the code earlier when we were doing this. We can still you can just continue. Now, so you get the inverse of that. No, the square root. Get the square root. First of all, the square root, and then the inverse later. So getting the square root, we use the Euler's criterion. And what Euler's criterion says, and of course, when you're writing that code, the one I was looking for, you're using the Euler's criterion for quadratic residue. And what does it say? The Euler's criterion says that if you have an x, that is a number, to determine whether this number has a square root, we use the Fermat's little theorem. We take p, which in our case is 17, then subtract 1 from it, that is 16, then divide by 2. And then do this mod p. If the result is 1, then that number has a square root. If the result is 1, then that number has a square root. But if the result is -1, then that number has no square root. So that is what we want. In this case, what we are doing is want to determine if this what the value we've just obtained, which is 13, whether it has a square root. So just taking 13, then raise it to 8, and doing this mod 17, I want to see whether the result would be 1 or negative 1. Now, this can be done using the fast powering algorithm. You can do this shortly, very fast. You can, first of all, 13 raised to 1 is just 13. What about 13 raised to 2? 13 raised to 2, 169. But we are doing this mod 17. So you divide by 17, and 17 goes there 9 times. And the result, the remainder is 16, which is, of course, negative 1. 16 just negative 1. Oh, this was squared. Now, what about 13 raised to 4? 13 raised to 4 will be the same as 13 square. The same as 13 square squared. 13 square is negative 1. Then when you square that, you have 1. But what I want is 13 raised to 8. 13 raised to 8 will just be the same as 13 raised to 4 squared. But 13 raised to 4 is 1, so when you square that, you have a 1. So that tells me, therefore, that 13 is a quadratic residue. It has a square root. 13 has a square root. Now, therefore, all the 3 conditions have been satisfied, and we say that the form, the short Weierstrass form that had been given, therefore can be converted to Montgomery. So what we've been doing was just to finding out whether it can be converted to Montgomery. And the question was that if it can, then convert it. So for us to convert it, we only require the scaling factor only. Once we have the scaling factor, we substitute in our formula. So how do we get the scaling factor? Because that is the only thing we require. This is our scaling factor, the square root of this. So this is the same as the square root of 3. Our Z naught was 8. Our Z naught was 8. And our A was also 8. So this one, we just use a calculator. 8 square is 64 times 3. That is 192 plus 8. We had gotten 200. And then divide that by the 17, goes there 11 times. And the remainder, of course, is 13. So we have the square root of 13. We want the inverse of that square root. So what is inside the square root sign is just 13. But now want the square root of 13. This one I have to use the code. I have to use the code. Let me just look for it. The square root. Quadratic residue. Yeah, this one I've gotten it. I want for Finding square root. I've gotten it now this time. Now, of course, we can do the square root manually, but you see, we are looking at how we can deal with the huge values, of course, because of security. And so we need to know how to write codes that will then assist us get square roots. And this code, we had already looked at it earlier, using the knowledge of quadratic residue. So quadratic residue is what I've just showed you, that you take a number and then you raise it to p minus 1 divided by 2 mod p. If the result is 1, then that number has a square root. And if the result is not 1, if it's -1, then it means it has no square root. That is what I've just written here. That is quadratic residue. The quadratic residue. I've taken the exponent. The exponent is here. Raise it to p minus 1 divided by 2. And then the result that I get, do it mod p. Do it mod p. And if the result is 1, then it's true. It's true that that number is a quadratic residue mod p. Else, if the result is -1, -1 is just the same as p minus 1. For instance, where p is 17, -1 is the same as 16, which is p minus 1. So I've said else, if the result is p minus 1 or -1, then it's false. In other words, the number is not a residue, it's not a residue. It has no square root. So this part is just the one that is talking about all those. Although you have the other parts above, you have other parts. These other parts just listing quadratic residues. I was using it to list. So I don't know whether this one is for listing. Let me just see, just let me run it. Oh, this one was to list. This one is to list all the quadratic residues. Yeah, so this one is a listing. That is I had not looked at this because I'm seeing it. I'm seeing it list residues. So it was first of all working out. First of all doing this. The part I had already explained. And after that, it lists all the quadratic residues mod 17. That's not what I want. That is not what I want. What I wanted was the square root. So I took one that is listing the quadratic residues. Okay. I'm trying to see whether I have one for find the square root, whether it appears it's not near. Okay, so let's just do it. Let's just do it without the code because of time. So how do we get a square root without a code? One, the square root of 13. So I'll just show you how you then do it. Of course, the way we do it is the same way you then write the code to get the square root. Now, so we are doing it mod 17. So what do we know therefore? What we know therefore is that the square root of 13 is one of these numbers, 0, 1, 2, 3, not 1, 2 of these numbers. Because the square root there must be 2 numbers, all the way up to 16. So we just square these numbers and see whether any of them gives us 13. Just square and see. So this is our x square. We just square them and see whether any of them gives us 13. 0 square, of course, does not. 1 square, of course, does not. 2 square does not. 3 square does not give us 13. So we proceed. 5 square will give us 25. And we are doing it mod 17. So 25 mod 17, this is 8. Is it? Yeah, it's 8. 17 goes there, the remainder is 8. Now, if you do this, you'll reach at number 8. I've skipped 6. So when you reach 8, 8 square will give you 13. 9 square will also give you 13. Let's just confirm. Let's just confirm 9 square. 9 square, of course, is 81. Is 81. Divided by 17 goes there 4 times. Goes there 4 times. And the remainder is 13. So 9 square is 13. 8 square is 13. Let me just confirm 8 square. 8 square is 64. Divided by 17, it goes there 3 times. The remainder is 13. So these 2 numbers are the square root of 13. These 2 numbers are the square root of 13. Now, what we require is the inverse of the square root. What we require is the inverse of this square root, the inverse. So the inverse of 8. This one you can use the extended Euclidean algorithm to find the inverse of this. Now, so of course, just before we go there, we've already found the scaling factor as, no. We've already found the square root of 13, the square root of this. And another one, another square root, we found as 9. So we will first of all look at a scenario where we are using 8. So we'll begin by using 8, then later on come to using 9. These 2 will give us 2 different Montgomery equations. Now, I don't want to go into details of finding this inverse. Of course, we can do that. Let me assume we find the inverse using the extended Euclidean algorithm. Of course, we can also do it using a code, the Rust code. Now, I showed you how to find, I was, of course, doing it using the Fermat's-Little theorem. I was doing it using Fermat's-Little theorem. You find that the inverse of 8 is 15. Can just confirm 8 times 15 and see whether the result is 1. 8 times 15. 8 times 15 is 120. Divided by 17, goes there 7 times, and the remainder is 1. So the inverse of 8 is 15. That is our scaling factor. Now that we have the scaling factor, we can straight away write the Montgomery form of this Weierstrass equation, the Montgomery form. So where there is this, you put 15, where there is S, where there is S, put 15. This Z naught was our 8. The value we got when we were solving for X was our 8. So 15. So just substitute this and reduce them mod 17. Reduce them mod 17, and so you get, and you arrive at that. That is, if the scaling factor is 15 and our square root there was 8, when the square root is, so we got the 2 square roots. One was 8, another one was 9. So we'll come back for 9. But now, what are the points for this? This is our Montgomery question. You can find the points. You can find the points for this curve. Now, to find the points for this curve, we will want to write it in this form. We want to write in the form y square, this form. So that means you multiply both sides by the inverse of 15. If the inverse of 8 was 15, then the inverse of 15 is 8. We found the inverse of 8 to be 15. That means the inverse of 15 is 8. So when you multiply by 8 both sides, multiply here by 8, by 8, by 8, by 8. What do you arrive at? You arrive at, this one gives us 1. So 1 times y square will be y square. Then 8 times x cubed will be 8x cubed. 8 times 3 will be 24. 24 mod 17 is 7. Then 8 times x will be 8x. So I'm just doing this so I can now find the coordinates, the points of this Montgomery. So how are we finding the points? How are we finding the points, therefore? We are doing it mod 17. We are doing it mod 17. So when x is 0, what is y? Just put here 0, 0, 0, and then y will also be 0. When x is 1, so what is the point? The point, therefore, when x is 0 and y is 0, the point is 0, 0. Now, when x is 1, put 1, 1, 1, you have 8 plus 7, which is 15. 15 plus 8, that is 23. Mod 17, that will be 6. But remember, this is y square. So y square is 6. So with your code, you find the square root of 6 to be y. The square root of 6, it will now be y. When I did that, I discovered that when x is 1, you cannot find the square root of that 6. You cannot find it. So when x is 1, there is no corresponding y value. When x is 2, there is no corresponding y value. And 3, again, there's no corresponding. So we can only find when x is 5. X is 7, we find the corresponding y values, and so on. So that is, then you come up with the code, all the points. Now these points, when we began, the equation we began with, which was the short Weierstrass, had 16 points. So that means, therefore, that the Montgomery question will also have the same points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the Montgomery, the points must be the same as the points, the same number of points as the one in the short waist arrays. So there must be the same number of points. Now, so when we've earlier on found the square root as 8 and 9. So we've used 8, and this is where we've reached. So we go back and now choose 9. Choose 9, so that S is the square root, the inverse of 9. The inverse of 9 is 2. Because 2 times 9 mod 17 is 1. 2 times 9 mod 17 is 1. So the inverse of 9 is 2. So the 2 now is our S. We form a Montgomery equation using 2. S is 2. So when S is 2, we would have 2y squared is x cubed. Then 2 times 8 times 2. No, this is 3. 3 times 8 times 2. 14. Now, if you want to get the points for this curve, again, you will multiply through by the inverse of 2, which we still have here. The inverse of 2 is just 9. So you will multiply by 9 the whole equation. And this will give you y squared is 9x cubed. 9 times 14. 14 is negative 3. That's negative 27. Is it 10? Something around 10 or what? You can do that because there's been negative 27 plus 17. This will be what? Negative 10. Then plus 17 should be 7. Yeah, that is what I was getting. So that is how you then convert it to this form. And when you convert it to this form, you can easily get the points corresponding to this curve. So just ask yourself, when x is 0, what is the corresponding y value? When x is 1, what is the corresponding y value? There are places where the values of x will not have corresponding y values, and so those ones they're not the ones we're looking for. We go for the ones that will give us the corresponding y values. In this case, 0 gave us, 1 gave us, 2 gave us a corresponding y values, 4 did not, 3 did not, 5 did, 6 did not, 8 gave us, and so on. So again, when you count these points, you would still find that they are also, you would find that these points are 16. You find that these points are 16. Any question up to there? Anybody who has not followed up so that we again explain? Yes, anybody who has not followed up? Any question or any comment? Now, so we've just seen how to convert the short waist arrays to Montgomery. Now, how do you convert Montgomery to short waist arrays? Now, this one is still converting from short waist arrays to Montgomery, and I'll skip it. of course, but the notes will have it. It's the same working. I only need to emphasize that if you're given this, you must know what it means. We are doing it mod 13. It means that this is our value of A, and this is our value of B. Our value of A and B. So you can easily write the equation for that. Now, you know what we're supposed to do to this question. What we're supposed to do is, we've been given this short waist arrest. I want to see whether it can be converted to Montgomery. So first of all, we have to check the three conditions if they are satisfied. And if they are satisfied, we proceed and calculate the scaling factor and substitute into our formulas. Now, you can even go further. The question has not asked for that, but you can go further and find the points of that Montgomery curve that you will have obtained. You can go further and obtain those points. Of course, those points are very important to us. When you're looking at point addition, you must have them to do point addition and so on. That is why we're going further and finding out those points. For the sake of point addition, point doubling, and so on, if you're asked to add those points on the curve, you should be able to know how to get them. Now, I'll just repeat what the three properties we're looking for. Been given this curve, and the question is it convertible to Montgomery? So first of all, we find out how many points does it have? How many points? What is the order of the group that it forms? What is the order? So when I did that, I found the order was 20. 20 is divisible by 4. So that is okay. The first condition has been met. First condition has been met. Now you proceed the second condition. You take this polynomial. Take this polynomial, equate to 0, and see whether you can find the value of x. If the value of x exists, find out whether the value of x exists. That's what I was doing here. By converting to equating to 0, I found that x can be 4. So what I mean is, you're substituting the values. You see, this one we are doing it mod 13. So you're substituting here 0, 1, 2, 3, all the way up to 12. And you want to see which of these would give you 0. So when you try to substitute 0 in this equation, you get 0 cubed plus 8, 0 plus, gives you 8. And 8 is not 0. So that means 0 is not a root. You try 1. So 1 cubed will be 1 plus 8 plus 8. This is 16, 17, mod 13. That will be 4. Mod 13, that will be 4. And again, this means that 1 is not a root, because we want it to give us 0. So let me now try 4. It will be 4 cubed plus 8 multiplied by 4, then plus 8. And of course, when you do this, you get 0. When you do that, you get 0. Yes, you get 0, because this will be, the first bit here is 16 times 4. And the second bit here is negative 5 times 4. And this one is negative 5. We are doing it mod 13. So 16 mod 13, that would be 3. 3 times 4, that would be 12. Then minus 20. Then minus 5. Is it? Have I done it correctly? Okay, this was 16 times 4. Mod 13, that would be 3 times 4, that would be 12. Then 8 here, mod 13, the same as negative 5. Then times 4, that would be negative 20. Then 8, it's just the same as negative 5. So what do we have here? This is negative 8, negative 5, which is negative 13, which is 0. Because we are doing it mod 13. So 13 goes into negative 13. The remainder is 0. The remainder is 0. So that means, therefore, 4 is a root to this, to the quadratic equation there. Not quadratic, it's a polynomial, to that polynomial. Because this is a cubic equation, it's not quadratic. It's a cubic equation. So I can use, let me refer to it as a polynomial. So 4 is a root to this polynomial. And that was our second condition. Because our second condition was to check whether this polynomial has a root. And once that is done, you take that root, which is 4, multiply by 3, square that root and then multiply by 3, then add a to it. Of course, a is 8 in this case. And that is what is happening at this point. And I got 4, mod 13. Now, the essence of this step is to check whether this is a quadratic residue. Check whether it has a square root. And using the Euler criterion that we talked about, we want to see if we can get a number. Oh, no, okay. Want to check whether this, so what was this? This is 4. So want to check whether 4 raise it to p minus 1 divided by 2 mod p gives us 1. So if it gives us 1, then it means this 4 here has a square root. But if it gives us negative 1, it means this 4 has no square root. So this is 4, p is 13, 16, that is 12 mod 13. Now, if you do this, you can get that it has a 1. It gives us 1. So that means 4 has square root. At this point, there's no need to find the square root. Just determining if it has square root. And then if it has, we say that our 3 conditions have been met. And since they have been met, it means therefore we can proceed and convert the equation given to us to Montgomery. So the steps I was doing here were just to ascertain whether it is quadratic residue, whether it has square roots. Now I found that the square root, and therefore the second thing that I'm supposed to do is to find the scaling factor. So the scaling factor is the square root, the inverse of this square root. The inverse of this square root. This one squared, and what was our z naught? Our z naught was 4. Our z naught was 4. 4 square is 16. 16 times 3, then plus 8. Now, 16 times 3 plus 8. That answer, I found it to be 4. Because you are doing it mod 13. So it's 16 times 16 times 3, then plus 8. What is it? 16 mod 13 is just 3. And then this is also 3. Then this is also 3. Then this is negative 5. So 3 times 3 is 9. 9 mod 13. 9 mod 13 is negative 4. Then times 3. Then minus 5. This is negative 12. Negative 17 mod 13. So what do you get? You convert it to positive number. You add 13 to it. So negative 17 plus 13 will be negative 4. Is it? Negative 4. Is it? Is it negative 4? Okay, let me just again check. This will be this 16 mod 13, which is 3. Then this is negative 5. So this is 9. I think 9 mod 13 is negative 4. When you subtract 13 from 9. Yes. Then times 3, then plus that. This, how was I getting this? This will be, okay, negative 12, negative 17. This one is giving me negative 4. Then plus 13, this would be 9 or what? How was I getting this for? I think I'm confusing somewhere here. Is working. I don't know whether I'm doing it correctly here. Just again write it properly. Oh, yes. There's something I was not doing. Okay, we are here. We are looking at what is here. Where was I getting 16 from? Where was the 16 coming from? It's supposed to be 3, and our Z was 4. Z naught. Oh, I squared and then squared. That is where the problem was coming from. I was wondering. I squared 4 to get 16. Then I again squared it. That's where the problem was coming from. So this is 12. 12, which is negative 1, times 4 plus 8. This is 4. Yes, that is 4. Oh, yes. Now I've seen. The problem was that I squared 4, got 16. Then again, I was squaring the 16. That is what the problem, that is why I was not getting the correct answer. Okay. Now that we've, what is under the square root as 4? Can we get the square root? The square root of 4 is plus or minus 2. This is the same as 2 and 11. 2 and 11. Because 2 will just be 2. But what about negative 2? Negative 2 would be 11. So 4 has 2 square roots, and these are the 2 square roots, 2 and 11. So I begin by choosing the first square root and find its inverse to give me S. So this, I'm using the extended Euclidean algorithm. Of course, we have a code for doing this. We have a code for doing this. So then when you do this, get the square root of 2 as 7. Not the square root, the inverse. The inverse of 2 as 7. Of course, that one is very easy because 7 times 2 is 1 mod 13. 7 times 2 is 1 mod 13. So that is our scaling factor. Once you have this scaling factor, you substitute in this equation and you have the Montgomery curve. Now, supposing you want points for this Montgomery curve, you could do the same thing you've been doing. Multiply this equation by the inverse of 7, which is 2. The inverse of 7, which is 2. Multiply through. When you multiply this by 2, get y squared. This one by 2 be 2y x cubed. And this one by 2 be 12 x squared. And this one by 2 be 2x. That is if you want to get points to this curve. So that then gives you this. And then you ask yourself, if x is 0, what's the corresponding y value? When x is 1, what is the corresponding y value? When x is 2, what's the corresponding y value? Of course, there are other values of x that will not give you the corresponding y values. Like in this case, you can see that when x is 6, there is no corresponding y value. When x is 11, you can see, and 12, there are no corresponding y values. What is important again to note is that the curve we began with, which was short Weierstrass curve, had 20 points. And so we expect this new curve to also have 20 points. Now, we go back. We took the case when under the square root, when the square root was 2, and we had denoted that the other square root is 11. So you can now go back and now find a square s, and s, which is the inverse of 11. And that is what I'm now doing here. And you find that the inverse of 11 in this case will be 6. And so if it's 6, again, back to this question, substitute 6 to find the corresponding Montgomery curve as this. And if you want points corresponding to this curve, multiply the entire curve by the inverse of 6. By the inverse of 6, which is 11. To get y squared is 11x cubed. This will be 77, but we are doing it mod 13, so you will reduce that. Then finally you have 11x. So 77 mod 13. 77 mod 13 is 12. And then the same way we've been doing, find the corresponding values of y for given x values. Good, that is how we convert from short Weierstrass to Montgomery. Of course, you first of all have to ascertain whether a given curve meets the 3 conditions. One, that its total points are divisible by 4. And 2, once you find that that has been met, you extract the polynomial on the right side and find out whether that polynomial has a root. And once that is ascertained that it has a root, take that root multiplied by 3 and then add a to the result. And the new result that you obtain, find out whether it has a square root. If it has a square root, that means that now the curve given to us meets the conditions. The next thing that follows is just to find the scaling factor. And once you have the scaling factor, you can substitute it into the equation, the formula that we have. Now, but converting Montgomery to Westeros is very easy. This one, as we began, I pointed out when it began that the formula will be this, that if you are given the Montgomery equation, this Montgomery equation, and you're asked to convert to short Westeros, what you require is to know that the short Westeros is a equation of this form. And use this formula where the first parts are equal and the second parts are also equal. So you find A is given by this fraction, 3 minus a square out of 3b square. And just getting them here, B is here, A is here. And what about B? B is given by this fraction. So that's what I did here. That's what I did. So I just substituted A, and my A in the question given to us, the question given to us here, A is 13 and B is 7. And we are doing it mod 17. A is 13, B is 7. So where there is A, I write 13. And where there is B, I write 7. Where there is A, I write 13. And where there is A, I write 13. Where there is B, I write 7. So when you do that, you arrive at this. This is where the only place that we can now work, because that means if I'm given this, I want to do away with the fraction. How do I do away with the fraction? You see, what do I have? What I have is 4 times the inverse of 11, x, 4 times. So I just find the inverse of 11 mod 17, the inverse of 13 mod 17. And the inverse of 11 mod 17 is 14. So what I have is 4 times the inverse of 11. This is the inverse of 11. This inverse of 11 using your code is 14. Then plus 10 multiplied by the inverse of 13. And the inverse of 13 using a code is 4. And then multiply this. Reduce mod 17. This, of course, will be 56x. 56x. Mod 17, that is 5x. And this, of course, will be 40. Mod 17, that will be 6. So you now have arrived at the short Westeros form. I've arrived at the short Westeros form. Now, so I just want to share the code. Of course, I'll not explain, but the code that does all this work for us. We want to convert from Montgomery to short Westeros, or you want to convert from short Westeros to Montgomery. You can have a code that will do all these things we are doing. In fact, the code can check for you the conditions, those 3 conditions, and proceed and calculate for you. So the Rust code that I'm sharing these notes converts the short waist array elliptic curve to Montgomery. So this code is supposed to check for those 3 conditions. And then you give it the formula. So when you check, you can see that I've given it the formula for converting to Montgomery. I've told it that you'll take 3. Oh, this is, okay. This is not the formula for, this is where now you are checking for the square root, the scaling factor. We are checking the scaling factor. The scaling factor, remember the scaling factor was S is the square root of 3z0 square plus A. That's what I've said. I want to calculate the square root. But before that, I must get what is under the square root. First of all, get what is under the square root. And what is under the square root is 3 times z0 raised to 2 plus A. So this formula, you just give this code, and this code will be doing it for you. And you look at this other condition. You see, it's checking for the conditions. I've said, I want to convert the short waist arrays to Montgomery. But before that, it has to check the conditions. So this is the right-hand side of the equation. I want to check whether it has a root. I want to check whether it has a root. And so that is what I'm doing here. Checking whether it has a root. So I'm saying if z raised to power 3 plus a multiplied by z plus b mod p is 0. If it is 0, then it means that there's some z0. There's some z0. In other words, there is a root. If it is 0, then there's a root. So that's the first condition that it's checking, whether it is a 0 or not. And the second condition is here. So you give it all the conditions to check, all the conditions. Then you give it how to get the square root. This is how it's supposed to be getting the square root. This part is how to be getting the square root. You give it, it gives the square root. Then what about the inverse? You also tell it how to get the inverse. If the inverse is negative, you add p. And so on. So this code is supposed to do that. We also included the workings, the explanations for the code. So you go through the explanations for the code and then understand. And then after that, I've also included some exercise questions for you to try. Okay, thank you. That's what I wanted us to look at today.